Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by Swayam. In the previous sessions, we were discussing on different combinational circuits. During this lecture, let us explore one more combinational circuit to compare binary digits known as magnitude comparator. It is a combinational circuit used to compare magnitude of two quantities in order to determine relationship between those quantities. In simplest form, we can say that comparator determines whether two numbers are equal or not. A basic comparator is XOR gate. Why is it considered as basic comparator? The reason is clear from the truth table of XOR gate. The output of XOR gate is 1 if two inputs are not equal and 0 if two inputs are equal. This figure shows how the exclusive NOR gate can be used as a 2-bit comparator. See, if inputs to XNOR gate are 0, they are equal, so it produces output as 1. When inputs to XNOR gate are 1, then also they are equal and produces output as 1. When inputs to XNOR gate are 0 and 1, here the inputs are not equal and XNOR gate produces 0 in its output. Similarly, when inputs to XNOR gate are 1 and 0, then inputs are not equal and XNOR gate produces 0 in its output. So, we can compare two numbers with single bits using an XNOR gate. So, let us see how to compare binary numbers containing 2 bits each. In order to compare binary numbers containing 2 bits each, an additional exclusive NOR gate is required. Observe the logic diagram for comparison of 2-bit numbers. The two least significant bits of the two numbers are compared by gate G1 and the two most significant bits are compared by gate G2 as shown in figure. If the two numbers are equal, their corresponding bits must be the same, and then the output of each exclusive NOR gate will be a 1. If the corresponding sets of bits are not equal, a 0 occurs at the output of XNOR gate. What can we do to produce a single output? In order to produce a single output indicating an equality or inequality of two numbers, an AND gate can be combined with XNOR gates. The output of each exclusive NOR gate is applied to the AND gate input. When the two input bits for each XNOR gate are equal, that means when the corresponding bits are equal, the XNOR gate produces 1. These 1s becomes the input to the AND gate and thus results in a 1. When the two numbers are not equal, that means one or both sets of corresponding bits are unequal. A 0 appears on at least one input to the AND gate to produce a 0 on its output. Thus, the output of the AND gate indicates equality or 1 or inequality 0 of the two numbers. Let us consider the realization of a 2-bit comparator using an example. See how the comparison of two numbers 1 0 and 1 0 performed using a magnitude comparator. The least significant bits of the two numbers 0 and 0 are fed into the first XNOR gate, which produces output 1 as those bits are equal. Then the two most significant bits of the two numbers 1 and 1 are fed into second XNOR gate, which also produces the output 1 as they are equal. Outputs from the XNOR gates 1 and 1 are then sent to AND gate, which results a 1 indicating two numbers are equal. One more example. Consider how comparison of two numbers 1 1 and 1 0 is performed using a magnitude comparator. In this problem, The least significant bits are 1 and 0 and the most significant bits are 1. To the first XNOR gate, the least significant bits of the two numbers 1 and 0 are fed, which produces the output 0 because those bits are unequal. To the second XNOR gate, the most significant bits of the two numbers 1 and 1 are fed, which produces output 1 as those bits are equal. These outputs from XNOR gates act as inputs to the AND gate and produces 0, which shows that the numbers are unequal. The basic comparator can be expanded to any number of bits. To compare two numbers with 3 bits each, we need 3 XNOR gates whose outputs are fed into AND gate. The figure here shows comparator to compare equality of two 4-bit numbers. Consider first number A with bits A3, A2, A1, A0 and second number B with bits B3, B2, B1 and B0. The inputs A0 and B0 is fed into first XNOR gate. Inputs A1 and B1 is to second XNOR gate. Inputs A2 and B2 is fed into third XNOR gate and inputs A3 and B3 is fed into fourth XNOR gate. Each XNOR gate checks for equality. The output of XNOR gates is finally given to an AND gate, which produces the final result as 1 only if A0 equal to B0, A1 equal to B1, A2 equal to B2 and A3 equal to B3. Now, it is the turn to implement both equality and inequality together using comparator. So, in addition to the equality output, fixed function comparator can provide additional outputs that indicate which of the two binary numbers being compared are larger. That means, there will be an output that indicates when number A greater than B and an output that indicates when number A is less than B. To determine inequality between two binary numbers A and B, we start examining from the highest order bit. Let A be a 3-bit number represented in bits as A2, A1, A0. A2 is the most significant bit or the highest order bit and A0 is the least significant bit. And for a 3-bit number B, bits are in order B2, B1, B0. If A2 equal to 1 and B2 equal to 0, number A is greater than number B. If A2 equal to 0 and B2 equal to 1, number A is less than the number B. And if A2 equal to B2, then you must examine the next lower bit position for an inequality. That is, we examine A1 and B1. Consider how comparison of two numbers A equal to 110 and B equal to 101 performed using a magnitude comparator. First, both higher order bits 1 and 1 are compared. Since they are equal, the next bits 1 and 0 compared. Since A1 equal to 1 and B1 equal to 0, A greater than B will be the result. So, it is clear that the comparator check for inequality from a bit position starting with the highest order bits. When such an inequality is found, the relationship of the two numbers is established. Other inequalities in lower order bit position need not be considered. Therefore, we can say that in comparators, the highest order bits take precedence over lower order bits. We start with 2-bit comparator. A 2-bit comparator to check equality and inequality will perform its operations as shown in the logic symbol given here. Here, the two input bits are A and B. It produces 3 outputs for conditions A equal to B, A greater than B and A less than B. The 2-bit comparator can be more conveniently described using the truth table. When A equal to 0 and B equal to 0, the outputs A less than B equal to 0 and A equal to B equal to 1 and A greater than B equal to 0. When A equal to 0 and B equal to 1, the outputs A less than B takes 1, A equal to B takes 0 and A greater than B takes the value 0. And when A equal to 1 and B equal to 0, the outputs A less than B takes the value 0, A equal to B takes the value 0 and A greater than B takes the value 1. And when A equal to 1 and B equal to 1, the outputs A less than B takes the value 0, A equal to B gets 1 and A greater than B gets 0. So, here A equal to B produces output 1 when A and B are equal, 0 in all other cases. When A equal to 1 and B equal to 0, A greater than B output produces output 1. When A equal to 0, B equal to 1, A less than B output produces output 1. The logic expression for each case, A less than B, A greater than B and A equal to B, can be derived from K-maps. Draw the K-map for A greater than B, a single 1 in the cell 1 0. That is all. From the K-map plotted here, the logic expression for relation A greater than B is A B complement. Draw the K-map for A less than B, a single 1 in the cell 0 1. From the K-map plotted here, logic expression for relation A less than B is A complement B. Draw the K-map for A equal to B, two 1s in 0 0 and 1 1 cells. And the logic expression for relation A equal to B is A complement B complement plus AB, which is A XNOR B. We can implement these expressions using logic gates. The logic expression for the condition A equal to B is A XNOR B. So, use an XNOR gate with two inputs A and B. To implement A greater than B, use the expression A B complement. So, use an AND gate with two inputs A and inverted B. Then, to implement logic expression for A less than B, input inverted A and B to an AND gate, which will produce A complement B. Now, we have learnt how to compare for equality and inequality of 2 bits. Next topic is a comparator used to compare two binary numbers, each of 2 bits. It is called a 2-bit magnitude comparator. It consists of 4 inputs and 3 outputs and generates less than, equal to and greater than inequalities between two binary numbers. First of all, let us construct the truth table and derive expressions for each inequality. The 4 inputs are A1, A0 belongs to the first number and B1, B0 belongs to the second number, and outputs are A less than B, A equal to B and A greater than B. Then, by looking into the input values, we will be able to write each output. When A is 0 0 and B is 0 0, the outputs are 0, 1 and 0 in the order A less than B, A equal to B and A greater than B. And the next A is 0 0, B is 0 1, the outputs are 1 0 0. Then A is 0 0 and B is 1 0, the outputs are 1 0 0. Then A is 0 0, B is 1 1, the outputs are 1 0 0. The next 0 1 0 0, the outputs are 0 0 1. Then 0 1 0 1, 0 1 0 the outputs. Then 0 1 1 0, the outputs are 1 0 0. Then 0 1 1 1, the outputs are 1 0 0, then 1 0 0 0, the outputs are 0 0 1. Then if A is 1 0 and B is 0 1, A less than B is 0, A equal to B is 0 and A greater than B is 1. Again, if A is 1 0 and B is 1 0, the outputs are 0 1 0. A is 1 0 and B is 1 1, the outputs are 1 0 0. A is 1 1 and B is 0 0, the outputs are 0 0 1. A is 1 1 and B is 0 1, the results are 0 0 1. A is 1 1, B is 1 0, the results are 0 0 1. And the last case, when A is 1 1 and B is 1 1, A less than B is 0, A equal to B is 1 and A greater than B equal to 0. From the truth table, let us compute logic expressions for outputs A greater than B, A equal to B and A less than B using K-map. Here is the K-map for A greater than B. After plotting values in K-map and grouping ones, we obtain the logic expression A greater than B as A1 B1 complement plus A0 B1 complement B0 complement plus A1 A0 B0 complement. The next, K-map of output A equal to B. After plotting values in the K-map and grouping ones, the logic expression obtained for equality A equal to B is A1 complement A0 complement B1 complement B0 complement plus A1 complement A0 B1 complement B0 plus A1 A0 B1 B0 plus A1 A0 complement B1 B0 complement. We can again simplify this Boolean expression by introducing XNOR function. A1 complement B1 complement is taken out from the first two terms and A1 B1 from last two terms. Then we rewrite the expression as A1 complement B1 complement dot A0 complement B0 complement plus A0 B0 plus A1 B1 dot A0 B0 plus A0 complement B0 complement, which is equal to A0 B0 plus A0 complement B0 complement dot A1 B1 plus A1 complement B1 complement. This can again be simplified into A0 XNOR B0 dot A1 XNOR B1. Thus, Boolean expression for equality condition A equal to B is A0 XNOR B0 dot A1 XNOR B1. The next is to derive expression for the inequality A less than B using K-map. After plotting values in the K-map and grouping ones, the logic expression obtained for the output A less than B is A1 complement B1 plus A0 complement B1 B0 plus A1 complement A0 complement B0. Let me bring out all expressions together. A greater than B is A1 B1 complement plus A0 B1 complement B0 complement plus A1 A0 B0 complement. A equal to can be expressed as A0 XNOR B0 dot A1 XNOR B1 and A less than B can be expressed as A1 complement B1 plus A0 complement B1 B0 plus A1 complement A0 complement B0. Using these expressions, we can design the logic circuit for 2-bit magnitude comparator. The first expression A less than B is implemented with 3 AND and 1 OR gate. Next, A equal to B is implemented with 2 XNOR and 1 AND gate. And the last, A greater than B is implemented with 3 AND gates and 1 OR gate. Now, you may find it crazy to design circuits. It's really amazing. Shall we jump into a 4-bit comparator with inequality? A comparator used to compare two binary numbers each of 4 bits is called a 4-bit magnitude comparator. The logic symbol of 4-bit comparator with inequality is shown here. Here also, to determine the inequality of binary numbers A and B, we first examine the highest order bit in each number. If A3 equal to 1 and B3 equal to 0, number A is greater than number B. If A3 equal to 0 and B3 equal to 1, number A is less than number B. If A3 equal to B3, then you must examine the next lower order bit position for an inequality. In case of 4-bit comparator with inequality, there are 8 inputs and 3 outputs. Before getting into a detailed study, let us check what are the comparator outputs when A3, A2, A1, A0 equal to 1, 0, 0, 1 and B3, B2, B1, B0 equal to 1, 0, 1, 0. Here, first A3 and B3 are compared. In this example, A3 equal to 1 and B3 equal to 1. Since they are equal, next bits A2 and B2 are compared. A2 equal to 0 and B2 equal to 0. Since they are equal, again next bits A1 and B1 are to be compared, and here A1 equal to 0 and B1 equal to 1. Therefore, we conclude that A is less than B. The value of 3 outputs of comparator will be A less than B equal to 1, A equal to B is 0 and A greater than B is 0. That is, the output A less than B is high and the other outputs are low. The truth table of a 4-bit comparator is given here. Here H denotes high voltage level and L denotes low voltage level. X is don't care. When you observe truth table, the condition of A greater than B equal to 1 is possible in 4 cases. And what are they? A is greater than B if A3 equal to 1 and B3 equal to 0, A3 equal to B3 and A2 equal to 1 and B2 equal to 0. The next A3 equal to B3, A2 equal to B2 and A1 equal to 1 and B1 equal to 0, and the last case when A3 equal to B3, A2 equal to B2, A1 equal to B1 and A0 equal to 1 and B0 equal to 0. So, its logical expression can be denoted as A greater than B equal to A3 B3 complement plus A2 B2 complement plus A1 B1 complement plus A0 B0 complement. Similarly, the condition for A less than B equal to 1 can be possible in the following 4 cases. What are they? If A3 equal to 0 and B3 equal to 1. Then the next case A3 equal to B3, A2 equal to 0 and B2 equal to 1. Next A3 equal to B3, A2 equal to B2 and A1 equal to 0 and B1 equal to 1. And the last case A3 equal to B3, A2 equal to B2, A1 equal to B1 and A0 equal to 0 and B0 equal to 1. So, its logic expression can be denoted as A less than B equal to A3 complement B3 plus A2 complement B2 plus A1 complement B1 plus A0 complement B0. The condition of A equal to B is possible only when A3 equal to 1 and B3 equal to 1, A2 and B2 are 1s, A1 and B1 are 1s and A0 and B0 are 1s, or when A3 equal to 0 and B3 equal to 0, A2 equal to 0 and B2 equal to 0, A1 equal to 0 and B1 equal to 0 and A0 and B0 are equal to 0. So, logic expression for A equal to B can be denoted as A3 XNOR B3 and A2 XNOR B2 and A1 XNOR B1 and A0 XNOR B0. Now, let us draw the logic diagram of 4-bit comparator. To get output A greater than B, perform operation A3 B3 complement or A2 B2 complement or A1 B1 complement or A0 B0 complement. To get output A less than B, perform the operation A3 complement B3 or A2 complement B2 or A1 complement B1 or A0 complement B0. To get output A equal to B, perform the operation A3 XNOR B3 and A2 XNOR B2 and A1 XNOR B1 and A0 XNOR B0. Please note, NOT gates are avoided in the logic diagram and represented by complemented input to reduce complexity of the diagram. So, it is time to end up. Let me summarize. In today's session, a combinational circuit to compare numbers was discussed, and that circuit was magnitude comparator. The magnitude comparator is a combinational circuit to compare magnitude of two quantities in order to determine relationship between those quantities. We have discussed single bit comparator, 2-bit comparator, 3-bit comparator and 4-bit comparator. Also, we discussed comparators to check inequality, and you know, comparators are used in applications like password verification and biometric application systems in our day-to-day life. With this, we come to the end. Thank you for watching. See you in the next session. Bye.